Hey everyone, and welcome back to another studio review video. So in this video, what we're going to be doing is covering microcontrollers. So first though, we're going to go over some basic circuits laws, and then we're going to get into that main topic, which is microcontrollers. So the main purpose of this studio is basically as a gear up to Project 3, because we know that most, if not all of the projects are going to be using microcontrollers in some form. I think it's mostly going to be Arduino at this point, but we're still going to cover Arduino and Raspberry Pi so that you can choose between these two architectures when you're doing your own projects or in projects for this class. So my go-to is Raspberry Pi because it's a little bit more powerful than Arduino, but Arduino is still very powerful and very versatile, and it's a great tool that we're going to use for most of the projects in this class. So those are kind of the topics we're going to go over today. We're not going to spend a lot of time on those basic circuits laws that I'll talk about right in a few seconds here, just because we're going to do a much more complete job of this in Studio 7. So I'm going to kind of blaze through these things and not really go into any sort of depth, because it will end up being redundant, because we're going to go over it next time in much greater depth so you can fully appreciate the analog circuits concepts that we're going to be going over in this class. Okay, let's get into it. So basic circuits laws. The only purpose of this is really just so that you guys can understand the circuits, the very simple circuits that we're going to build so that we can demonstrate the functionality of these different microprocessor boards and the code that we're going to write. So we do need to build some circuits around our microprocessors so that we can actually use them. So we need to drive them. We need inputs, we need outputs. And so that is what we're going to be doing. That's the motivation behind this. So first things first, we've got some safety tips here. And there's a variety of things. I'm just going to touch on a few of them, but you can see them all on the slide here. So first things first, if you want to solder something, and if you go to Studio this week, you'll see we have a little board that we're using to make things a little bit easier and more consistent across studios that is soldered all together to make everything super rigid. So if you want to do stuff like that, which I encourage you to do, and in fact we will require you to do for certain projects if they're more circuits heavy projects, then you need to take the BW workshop so that you can get trained on how to solder, and so that you can go into that room and use the soldering equipment that we have. So things that they will teach you in that workshop, and by the way, I also teach that workshop, so please come and take it. We'll go over everything, and some of you already have, so that's great. But there's fumes, things are very hot if we're soldering things, right? We're melting metal. So you have to take that workshops regardless of whether you know how to solder or not, just so that we feel confident that nothing catastrophic is going to happen when you're soldering. So please take that workshop. Other things that I want to touch on in this long list of safety tips here. Being aware of static electricity is a great point that's listed on here that I think a lot of people really just ignore. So when you get a part that comes in a bag that says ESD with a label across it, and it comes in that sort of plastic bag that protects it from static discharge, or it says electrostatic discharge, caution, something like that, that's not something to just ignore. So please be aware of those things, because some parts are highly susceptible to being shocked. Shocks and static discharges can be thousands of volts, 10,000 volts, and that can seriously destroy a part if you manage to shock it. So this is especially important as we move into winter, because people are going to be wearing more clothing, and that's going to create static. So unfortunately, we don't have wristbands to plug into the lab benches here, and so you're just going to have to be as careful as you can. Don't work on carpet. Don't have a giant sweater on when you're soldering or working with parts. Things like that. Just try not to shock your parts, and be aware that some parts are extremely sensitive to that, and it'll tell you on the bag. It'll say ESD or electrostatic discharge, so just be aware of that. Do the math before you try it. Yeah, don't just plug parts in. The reality is when you start making circuits, things are going to break, especially if you are new to this, which I imagine all of you are. So things break. It happens to the best of us, but let's try not to make that happen, especially with more expensive parts. We want to be very careful. So do the math before you try it. Make sure you know how much voltage is going to go through something. Read the data sheet, how much current is going to go through something. What's the voltage drop across it? Make sure you know what you're doing before you do it. And read the data sheet on the part so that you know whether the part can handle what you're about to do to it. That's very important because a lot of people, I mean, data sheets are pretty boring, right? No one wants to read them, but you got to do it because otherwise you're going to ruin your part and you're not going to understand what your part can do. So make sure that you do that. Documentation is key here. Capacitors always lie, so this is just a note basically saying, hey, you never know what the charge stored on a capacitor is. That's not necessarily true, you may know. But as a safety tip, just know that if you have a large capacitor that can store a large amount of charge and you touch the leads across like your hand or something, it may shock you, depending on how big that capacitor is and how much charge it can store. This probably won't happen, but it's just a good note to be aware of. And in general, if you're not sure about something, ask us, that's why we're here. So those are just some safety tips. There's more here, you can read the list. Those are the ones that I wanted to touch on. Okay, so now for our very basic circuits review concepts, or not really review, but an introduction to some very basic concepts that you probably have seen before, but if not, that's fine, we're gonna go over them right now. So, basic units and concepts that you need to know. Voltage, current, resistance, and power, okay? So first up, voltage. This is electrical potential. Those are the same things. You can hear potential, you hear voltage. They're the same thing. Potential probably more clearly describes what voltage is. So the units on this is volt. It's sort of like pressure. So I'm going to try to draw an analogy to water flow because it's not a bad analogy actually. And so if you want to think about it in terms of something that's more familiar, like water flowing through a pipe, think about the pressure of the water in the pipe, okay? That's kind of like what voltage is, and we'll talk about this more and much more extensively in the next like 3 studios that we have set aside for circuits and electrical engineering concepts, okay? This studio is not that. This is about microcontrollers. But these are still good things we need to know just so we can set up the simple circuits that we're going to be talking about. Okay, current is all about electron flow rate. How many electrons are physically flowing through my circuit? Okay, and going back to that water flow analogy, how much water is flowing through my pipe? Okay, so voltage is like what's the water pressure? Current is like how much volume of water is flowing through the pipe, right? How many electrons are flowing through my wire or through my part or through my circuit, right? That's what current's about. Resistance is probably the easiest thing to understand intuitively. It's just resistance to flow, right? I'm restricting the movement of electrons through some component, okay? And we have resistors to do that, right? And this is just like, for example, if I had a blockage in my pipe, that might be a resistance. All right, power takes into account 2 things, voltage and current. So power is literally voltage times current when we're talking about electrical stuff, right? We've talked about power before when we talked about thermodynamics. This is a little bit different because we're talking about electric power. I mean, it's the same concept, but the formula is a little different. Now we want to talk about volts times current. So those 2 things. So just be aware of that. For example, you know, when you shock yourself, everyone's gotten shocked before. That's a few thousand volts, but the current is super low. So it's still low power. It's not going to kill you, but it hurts because it's high voltage. Okay? And we'll talk more about this in the units and everything like that, although we've already sort of introduced that in the thermo session. But we'll talk more about power when we actually get to our electrical engineering section properly next week. But those are just things to be aware of. Okay? Ohm's law. I'm not going to go in depth on this. We're going to talk about this a lot. It seems very simple, and it is very simple, and that's kind of the beauty of it. It's just this basic relationship between voltage, current, and resistance. So, voltage equals current times resistance. V equals IR. You can rearrange that in a bunch of different ways, right? This is very important, very fundamental. It's something that you should memorize. If you haven't already memorized it, you'll be using it all the time. Okay? All right, so this slide is all about giving you intuition about what happens if I have too much or too little of the things we just talked about. So what happens if I have too much voltage? So if I have too much voltage, for example, if I have a transistor, and that's something that we'll talk about, so if you don't even know what a transistor is yet, that's fine. We're gonna talk about it next time. But basically transistors, or at least MOSFETs, have gates. And so if you apply a very large voltage to the gate of a MOSFET, then you may short the gate to the rest of the MOSFET, the body of the MOSFET. And if you do that, then you will destroy the MOSFET. Similarly, a little bit simpler example. If I have a resistor and I have a huge potential difference across the resistor, I may very well just blow that resistor. Or a capacitor, same thing. When I have super high potential differences that I may not expect, that's where we can start blowing insulation and get current moving through our circuit in a way that we may not expect, okay? And that may be catastrophic. All right, so that's what we want to watch out for. That's why this stuff is important. Current, too much current is going to lead to heating. And that is the image that you see on the slide here. So this is actually something that I was working on over the summer, and this is a FLIR thermal image of a circuit test setup. So right here, what's going on is this amplifier is heating up. So it's driving a super low resistance load. And so there's a lot of current, go back to Ohm's law, right? So if I have a super low resistance load, I'm gonna have a lot of current going through that load. And so that amplifier is doing a lot of work, it's heating up quite a bit. And that load is heating up too. So there's a lot of current, things are starting to heat up. That's where things can start to break or melt or break down. So we have to be aware of that, and you can see there's a lot of hardware around that amplifier to keep it cool. There's a fan here. The thing that's actually heating up that you can see in the image is a heat sink to try to dissipate some of the heat as well. So these are things to be aware of. Resistance, if you have too much resistance, then you're just not going to get a lot of current flow where you might expect to get current flow in your circuit. Things may not work out in the way that you expect. But the real problem comes when you have too little resistance. For example, in our circuit that we're going to set up in this studio, you will see an LED that we're lighting up. It's very simple. That's what we're going to be doing. But there's a resistor between the LED in series with the LED so that we can have some voltage drop across that resistor so that we have less current flowing through the LED. If we just put all of that current flowing right through the LED has very low resistance, so we're gonna get a lot of current, and that will blow up the LED. So if you've ever hooked up an LED to like a 9-volt battery, just like one of those handheld little 9-volt batteries, you'll know that if you do that, the LED turns on for a minute and then it breaks because it can't really handle the amount of current going through it. You have to drop some of the voltage across a resistor so that you don't have as much current flowing through that LED. Okay? Short circuiting just kind of refers to a situation where I accidentally have some sort of electrical connection in my circuit that I don't expect. Okay? So for example, if I have a circuit board laid out that I've soldered up and I accidentally like drop a wire, like let's say I was cutting some wire and I dropped it and it just happened to connect across ground and the positive power line, now I have a short, it's probably gonna melt, okay? Or cause some sparks and blow out of there. So these are things we want to avoid. We want to really make sure that when we're soldering things or making connections that we don't have connections between areas that we don't expect. So you wanna double check things because otherwise you can have this situation where you might have too much current flowing through something and you can blow something up or just heat it up way more than you expect or something like that. A lot of times these mistakes are catastrophic and they blow parts. So just be aware of that. Okay, quick rundown on some electrical components. Once again, we're gonna talk a lot more about these things, so I'm gonna blow through this. But resistors, right, just cause potential drops in my circuit, right? They resist electron flow. LEDs are just specialty diodes. They stand for light emitting diode. And a diode is basically a component that allows current to flow in only one direction in my circuit. There's more to be said about that. And there's many different types of diodes, but we're gonna keep this simple and just leave it at that, okay? Transistors we're not gonna be using today at all, and we'll talk a lot more about transistors later because this is such an important component that can add a lot of complexity and functionality to our circuits, both in analog and digital circuits, okay? But with a MOSFET, we're talking about a voltage controlled current source. So basically I put a voltage at the gate of this device and it controls the current flowing through two terminals, okay? If we're talking about a bipolar transistor, BJT, then it's a current controlled current source. Okay, so how much current is flowing through that gate region? Well, not the gate. In that case, it becomes the base, and then the collector and emitter regions, how much current is flowing through there. So I get to control the current flowing through the collector and emitter regions based on the current flowing through the base, okay? Capacitors are all about storing charge, but their function in doing so, they allow us to smooth signals. We can create filters with capacitors, and we'll talk about the impedance of a capacitor in a few studios, okay? Inductors store energy in a magnetic field. That's all I'm going to say about that, and we'll talk about it later, okay? All right, testing, basic test equipment. Multimeters, very important, very basic, very fundamental. You'll see them in the lab. We have large multimeter, like bench multimeters. They kind of look like this thing that's in the image here. And so you can do like a 4-wire measurement, for example, if you want to measure some resistance really accurately. Or you can just use this as a voltmeter or a current meter, etc. Okay? So multimeters just basically let you measure a variety of things. You've probably seen those little handheld ones where you just spin the dial. You can see that on the slide here. And you can kind of switch it into different modes like the ohm meter or the amp meter or the voltmeter, okay, and so on. Okay, so they just let you measure a variety of things. All right, so bench supplies are something that you all will be using in your projects in Project 3 to provide power to your circuits, assuming that you choose a circuits-based project. So for example, I'm gonna plug the blood pressure cuff project right now because this project is great for learning about embedded systems and circuits in general, analog circuit concepts even as well, which I'm very happy about. So yeah, bench supplies, very useful. Basically act like a battery, except that you can change the voltage on your terminals. And yeah, so they're basically just like a fancy battery. They're just a power supply. That's all they are, okay? All right, let's get into the main thing that we're gonna talk about now. Okay, so that was all sort of preliminary stuff that we needed to understand. Now let's get into the bulk of this, okay? Microcontrollers. So first things first, what is a microcontroller? So on the slide here we see microcontroller is basically compact integrated circuit designed to govern a specific operation in an embedded system. Okay, so they control tasks based on however you program them to do so. And we have something like an Arduino, we have a variety of pins that we can hook up to, and we have different I/O interfaces, and we'll talk about all that stuff as we go forward, okay? So microcontrollers are everywhere. That's kind of the motivation behind this, besides the fact that you'll be using it in your projects. Microcontrollers are used in everything, especially nowadays in the digital world that we live in at this point. Microcontrollers are just used for about everything, okay? Of course, in your computer, in your phone, in your iPad that you might use to take notes, in your camera, in your car, you can see a giant list of things that use microcontrollers in a car. So there are many, many microcontrollers in each of these devices that I'm talking about. And yeah, so very important, very widespread, universal across every bit of modern technology. Okay, so this slide gives us kind of a basic breakdown of what is in a microcontroller, okay? So microcontroller is a very, very broad term, could apply to a variety of things that do computation, okay? When we're talking about something like an Arduino, we might see something like this. This is sort of the standard stuff that you might find in a microcontroller. So first things first, one of the most important things, although all of them are important, right? But the CPU is where all the computation actually takes place. So people often refer to this as like the brains of the microcontroller. That's pretty accurate. This is where all of your computation takes place. And you can actually take classes at Brown to design CPUs, which is really cool. And you can do that in classes like 1640. So if you want to learn about that, go take 1640 and you'll actually get to design your own CPUs. Okay, you actually get to design several CPUs. So very cool. Yeah, so there's a lot that goes into that I can't talk about right now because we'll spend this entire class and beyond talking about CPUs. Okay? All right, ROM and RAM. So ROM is read-only memory. So this is something that your CPU is going to read one time it's basically the list of instructions that your CPU is going to execute, okay? So in the case of an Arduino, what we do is we program the Arduino from like your MacBook, your laptop, right? You send it something when you press run. What happens is that code goes to an electronically erasable ROM, so a special type of ROM that can be erased, and that becomes the instructions for your code. So now the cool thing about having an electronically erasable ROM is that you can send code to your Arduino and then unplug it from your computer and go just supply power to it some other way, and we'll talk about how to supply power to an Arduino as we go forward. But that code remains on your Arduino in its ROM, okay? So it doesn't need your computer to run the code. All right, so RAM is like the memory where your code is going to be dynamically storing things when it runs, if your code requires that. The code that we're gonna go over today does not. But for example, if I'm taking in, some values from a sensor, let's say I'm monitoring temperature, okay? That's what I'm building. I'm building some temperature monitoring system. Okay, so if I leave my microcontroller and I tell it I want to know the temperature every hour. So every hour your microcontroller boots up, well, it doesn't boot up, but it takes a measurement from the temperature and it stores that in RAM. So that you have a list of all the temperatures for every hour, okay? So something like that is an example of where you might use RAM. It's just more memory, but it's something that your code can actually access and store values in. And it can also read from RAM as well, okay? And all that's gonna happen in the CPU. So the CPU is gonna say, okay, I'm gonna go to this address in RAM and read this value, or I'm gonna go to this address in RAM and write a value, okay? All right, so IO ports, this is how we interface with the outside world, okay? So if we don't have IO ports, then our CPU isn't really going to be able to do much as far as interacting with stuff around us. So we need some inputs, we need some outputs. That's what IO pins are all about, input-output pins, right? So you'll see in our example, we're gonna have an LED, that's our output, and we've got a toggle switch, and that is our input, okay? So that's what that's about. And there's some other things in here as well, but those are the things that we're gonna focus on for the purposes of this studio. Keep it a little bit simpler, okay? All right, so I just kind of went over all of this, everything that's on this slide, but quick run through again. So we talked about the CPU is kind of where all the arithmetic operations are taking place. Transfer between data and RAM is taking place. We're reading the instructions from ROM. Everything is happening through the CPU, right? The CPU is controlling everything that's going on with your microcontroller, okay? Memory, talked about that, ROM and RAM, right? We talked about those two types of things. Yeah. IO peripherals, same deal, right? We need some inputs, we need some outputs, okay? We need to take in information from the outside world, and then we need to process that information in the CPU, and we need to do something with it, okay? So that's what input and output peripherals are all about, okay? So an input peripheral, we might think of like a keyboard could be a peripheral, or a mouse could be a peripheral for your computer. In our case, it's a little bit simpler, but variety of things. Whatever you're hooking up to your microcontroller, that's the peripheral. That is the component that you're hooking up as a peripheral. Okay? All right. So now that we've gone over all of that, let's actually start talking about what Arduino is all about. Okay? So Arduino is just hardware, right? It's a hardware component. Specific microcontroller. It's got a variety of pins. A lot of them, they have different purposes that we'll talk about. A lot of them are general purpose, so we can do a variety of things with them. It has onboard memory. It's got an electronically erasable ROM. It has a USB interface so we can connect to the computer and send our code to the Arduino, which is pretty convenient, etc. Okay? Arduino is also software, so all of that goes into the hardware component of Arduino, and we're going to be using Arduino Uno. That's the one we're going to use. Arduino has a variety of products. You can check them out. We're just going to use the Uno because it's probably one of the more common ones, and lets us kind of do this a little bit more simply, okay? Software, on the software side, Arduino is actually its own language, okay? It's very similar to C or C++, but it is its own distinct language. So just keep that in mind. We're going to be using the Arduino IDE to write our code and compile it and upload it to the Arduino hardware. So when we talk about Arduino, we're referring to two things, hardware and software. All right, pins, okay? So pins are very important, and you can see a pin out diagram on the slide here. So pins can have a variety of functionality, and I'm going to zoom in on this diagram so you can see it a little bit better. So what do we have going on here? And we're going to talk more about this as we go on. But you can see, you know, we've got some plus 5 volt pins, we've got some plus 3.3 volt pins, we've got ground, we've got BN, so we can supply power to our Arduino. We've got some analog to digital converters. We've got a variety of GPIO pins, some digital pins. We've got some pins that are going to be used for communication protocols like I2C and SPI. And we've also got some pins down here, TX and RX. Those are going to be used for UART communication protocols, and so on, okay? So we're going to talk more about those things as we go, but just keep in mind that's what pins are all about. And that's the pinout that shows you what things you can connect where and what functionality different pins have. Okay, this is just a slide showing you some motivation behind why Arduino is a great thing to learn. There are a variety of different projects. I'm sure that you are all aware of this, but you can look into this on YouTube, for example. Lots of people doing a lot of different cool projects with Arduino, and you're going to be doing cool projects in this class too. So you'll get to see that for yourself firsthand, okay? All right, now, how do we power the Arduino? Okay, so this is all great. We see why we're gonna use the Arduino. We see we've got some different pins. We're seeing how the structure of the Arduino works exactly with this CPU and ROM and RAM and these peripherals that we're gonna hook up to it. How do we turn the thing on, okay? So, with your computer, it's pretty easy, okay? You can just hook up to it with USB. Okay, so that makes it really simple. USB, no problem, okay? And you can do that. I'm gonna hold this up here so you can see. So the USB you'd plug into this right here, okay? So that's one way to do it. You can also use a barrel jack. The barrel jack is this thing right here, okay? So that's something that you can do. It's on the Arduino Uno. It's not on every Arduino, but this one has both. So it has options. You've got this and you've got the barrel jack. The USB port is nice because you can also send all of your code to it, to the Arduino through it. Okay, so you can power it and send the code through just this one connection right here. It also has a VN pin. Okay, so VN, if I look at the pins, they're also labeled on the board, which is very convenient. This pin that I'm pointing to right here is VN. So it's very hard to see, but that pin is VN, okay? And you can see it on the slide here. As I zoomed in before, you can see moving my cursor right here, this is the VN pin, okay? And you can supply a variety of different voltage supplies to the Arduino. So it can run on 3.3, can run on 5, 9, 12, very versatile. It can do a lot of different things. It can support a lot of different supplies, okay? All right, so this is really just going over the same stuff that we did before, but I'm gonna zoom in on this again and go over it more slowly now. So this area is all about power, okay? So we've got our 3.3 volt out. So when I power my Arduino, I have an easy access to a 3.3 volt supply now, okay? So I can take a pin from that 3.3 and power something else with it, okay? No coding necessary. This is always just at 3.3 volts, okay? 5 volt pin, same thing, except at 5 volts, right? So this is an easy access to a 5 volt line, whatever I may need that for, no coding required, okay? Ground, another thing, easy, no coding required, 2 ground pins. These are very important, you'll use them a lot. VN is for powering the Arduino, right? As we just said, that pin is on the Arduino, as I showed. And so that is another way to power the Arduino without having to use the USB. So if you've tested all of your code and your project is good to go and you're ready to just power with like a battery and some, handheld device or whatever, then the VN pin might be the way to go once you've got all the details situated, okay? All right. Okay, so now we're gonna talk about the analog pins. So you saw those when I zoomed in, but we're gonna zoom in again. So the analog pins are all about taking signals that look like this. Okay, so this is this analog signal. You might see something like this coming from a sensor, for example, or like maybe a microphone might be a good example. When you speak, your speech may look something like this. It's gonna look like, a sinusoid of sorts, okay? And it's going to vary dynamically, just like this signal does, okay? So the analog pins are gonna let you take in that signal and process it into a form that the Arduino can understand so that you can do processing on it in your code. So this is very important, very useful in a variety of situations. And those pins, I'm gonna zoom in now, are right here, okay? So this is all about digitizing analog signals, all right? So different sensors, like I said, give an analog output, and we may need to digitize that so we can do processing on those signals, okay? Once again, I'm gonna bring up blood pressure cuff because I think it's a great project for learning about these topics, okay? They have a pressure transducer, and the signal from that pressure transducer needs to be digitized. And so to look at that pressure transducer signal, we bring it in through these analog to digital converter pins, okay? So that's another example. But all these pins are analog to digital converter pins, and so they have a special purpose, and that's just something to keep in mind, and that's what they're used for, okay? And by the way, we'll talk more about analog to digital conversion and what the difference is between analog and digital signals next time in our beginning to circuits studio, okay? All right, general purpose input output pins. These pins are used all the time, very useful for a variety of different things. So the main thing here is that they do say general purpose input output. So they can be an input or an output, okay? They're configurable. And these are digital pins, so they only are gonna be used for two values, on or off, okay? So they can be like 5 volts or ground, okay? Now within that you can do a lot, but just keep that in mind. They're either gonna take in high or low, and they're only gonna output high or low, okay? And those pins are right here. So you can see them, there's a lot of them. Anything that doesn't have a special purpose is going to be a GPIO pin. And we'll use some GPIO pins as well. Okay, pulse width modulation, very important concept, very useful, although it may seem a little bit weird at first, okay? So as I said, the digital pins can only supply high or low. But what if you want an analog type output, or you may not even want an analog type output, you may just want 2.5 volts out. Well, how do I do that? So what I can do in that case is I can turn my pin on for a period of time and then turn it off, and then turn it on and then turn it off. And depending on the duty cycle, so how long it's off, how long it's on, I can get different voltage levels, okay? So for example, at a 50% duty cycle, so what does that mean? In one period, one waveform period, it's on for 50% of the time and off for 50% of the time. So if my high voltage is 5 volts, then that means that I would average this out to be around 2.5 volts. So I'm getting around 2.5 volts out using pulse width modulation. Now, if I go down in the duty cycle, so now like 10% duty cycle, that means I'm on 10% of the time and I'm off 90% of the time, okay? On the flip side, if I go to something like an 80% duty cycle, now I'm on for 80% of the time and I'm off for 20% of the time, okay? So this is all about using sort of just the simple digital pins on or off to actually create a variety of different voltage levels. So you can do a lot with this. You can drive a motor, for example. That's a great application for this, and it's used a lot. Something like a Class D amplifier, which we're not going to talk about at all, but Class D amplifiers use pulse width modulation to amplify signals, okay? So the basic code here, or not the code, but the basic equation here that you can kind of use is just V out is equal to V max. So for example, in this example that I've been saying, 5 volts times the duty cycle. So 5 volts times 10% duty cycle is going to be half a volt. Okay, that's kind of what we're dealing with here. All right. So you can see the different pins listed: 3, 5, 6, 9, 10, and 11 on the Arduino Uno support PWM. And yeah, that's what they do. So just summing up what I said, they sort of replicate analog signals using these digital pins. You can even relay speech. You can drive a speaker with PWM. So all you do is you filter this digitized signal, and then you get everything kind of rounds off and averages out. And you're able to get some pretty clear speech and stuff like that. So a lot of speakers use Class D amplifiers, like I mentioned before, and those use PWM. So this is a very important concept, even though it may seem a little bit weird and a little bit abstract at first. But just remember in the name, right, pulses. So we have pulse, width, modulation. So we're changing the width, right? That's what we're modulating. All right. Okay. Drawing pinouts, I'm not going to spend a lot of time on this slide because this is really just saying, hey, when you do circuits or when you're designing your embedded circuit, just kind of draw out, right, like what is connecting to what on the Arduino. Okay, that's all this is really saying. It's not anything super crazy. Just look at the pinout, make sure you know where you're going to connect different things because you have to know that for coding reasons, of course, and we'll talk a little bit more about that later. But yeah, this isn't anything super complicated, so that's pretty much all for that. All right, so switches. Lots of different types of switches, if you will. So push buttons are one example, very easy example that you will see in the studio if you physically go to the studio this week. I'm not going to use a push button for the demos in this video, but for example, there's a push button right here, right? It's pretty simple, right? You just push it and it allows the electrical connection or doesn't, depending on whether you push it or not. Okay, and you can see an image of that right here. So this is a pretty common little push button that you'll probably see a lot. All right, relays. So a relay is this picture right here in the bottom corner. And you can kind of see here, basically, I see relays used a lot in sort of higher power systems. So for example, if you've ever driven a golf cart, when you press on the pedal, you hear like a click. That clicking sound is the relay contact slamming together. So how a relay works, right? I basically have 2 contacts and I want one of them to kind of slam into the next, and that completes the circuit. That's basically what it is. So it's a switch and it's powered electrically. So right here you can see this little coil symbol that I'm circling right here on the screen is basically an electromagnet. And when I turn that electromagnet on, it pulls the contact in a normally closed system, that is, it will pull the contact to the other contact because it is magnetic, okay? And that'll complete the circuit. So that's normally closed. So that means that normally when I'm not turning the electromagnet on, my relay will be off by default. That switch will be off. In a normally open system, it's the opposite. So if I had my switch normally over here, when I turn the electromagnet on, it'll pop over here, okay? So you can have both of those systems depending on how you configure the actual mechanical design of your relay. But that's what a relay is. It's very simple. It's just, I have a magnet that I turn on and off, and I can basically slam contacts into each other to complete the circuit, okay? Toggle. So a toggle switch is what we're going to be using for the demo, and you can see a picture of it on the slide, and I'll show it when we get to the demo part, but basically it's just a little switch. You switch back and forth, and that's all it is. When it's configured like this, these 2 pins are connected together, and when you flip it the other way, then these 2 pins are connected together. Okay, that's all it is. Slide, also very simple. I basically have these terminals and I slide this contact across them to complete the circuit. Okay, so there's a variety of ways basically to complete circuits. That's all we're talking about here. All right. Okay, now we're going to talk about how do I actually code the Arduino, okay? Which is like one of the most critical things that we need to go over. All right, so first things first, you're gonna need to get this Arduino IDE. So like I said, Arduino has its own software, its own language, and its own IDE. So you just download this IDE, and then we'll switch over to that in a second, but that is the main place where we're going to be coding everything for your Arduino, okay? All right, so as far as the structure of the code is concerned, there's basically going to be a setup area when you make a new sketch, they call it in the Arduino IDE. So there's going to be a setup section, and then there's going to be a loop section. We'll talk about loop on the next slide. Before we even get to setup, though, there's a few things that we need to do. So if you have any libraries that you're using, different, functions that you need in a specific library, you want to include those before setup. So you'll basically type hashtag symbol, include, and then you will include the name of the library. All right. Also defining pins. So you'll give pins a name. For example, switch in. It might be a name for your pin. So you'll put hashtag define, switch in, and then the actual number of that pin that you will find on the pinout. So the Arduino knows what values it assigns to what pins. So you can simply look up a pinout diagram, or even just look at the Arduino itself, and it has all of the pin numbers labeled for you. So you just need to put, hashtag define, switch in 3, for example. Okay, and we'll talk more about that when we actually start coding. All right, so we don't have any libraries, but we certainly will be defining pins. Also defining variables. So you can initialize variables here. For example, in the code on the slide here, you'll see these constants, const int, and then for example, it says servo speed equals 10. So this will be some constant that I've just given a name so that I can refer to it throughout the code. Okay. Also, you can see some ints here, just some basic integers. And these will be the initial values that I give these integers. They may or may not change depending on what I specify in my code, okay? Anything in setup so this was all before setup. Now within setup, this is stuff that's going to run just once, okay? That's the main thing with setup. It's gonna run one time, and then your Arduino is going to pop into the loop, and it's gonna stay there, okay? So within setup, you need to specify things like pin functionality, okay? And we'll do that when we do our demo in a few seconds here, or in a few minutes here, okay? Initial state of pins, initializing classes, initializing variables, anything that you need to do setup-wise that only runs one time, that's what you want to be doing in setup. All right. Now there's the loop. So this is where we read inputs, we do data processing, manipulations, whatever we need to do, and then we have our output, okay? So this is gonna be called over and over and over again very quickly at whatever, depending on how many lines you have within loop and your clock speed on the Arduino and stuff like that. But it's gonna be called just over and over again, okay? So if you have, an input, this is called polling. So for example, if I need to monitor pin 3 and see whether that value is high or low, that's what I put in the loop. I would put, pin 3 value equals, and then I read the value of pin 3, and then I can do some data processing and some if statements or whatever the case may be, and then I send the result to the output. So I will write to a different pin, for example. Okay, that might be something that you do. And that's called polling, where I just read inputs over and over again, and then I go manipulate an output based on whatever my code specifies, okay? But the main point here is this is gonna be called over and over again. That's why it's called loop. All right. So running the code, we're gonna just go ahead and jump over to the Arduino IDE here so that I can just show you this. But basically you're gonna specify your board, then you'll write your code, you'll compile it, then you'll upload it to the actual board, and then you will finally run everything, okay? So let's go ahead and pop over to the Arduino IDE so that I can sort of show you this explicitly. Okay. All right, so when you open up your Arduino IDE, you'll basically go to File, and then New Sketch, okay? And it'll open up a page that looks like this. I'm not gonna do that right now because it's gonna mess up this video, but you get the point. You just open up New Sketch, you click New Sketch, and it'll open up something that looks exactly like this. So now you can see what we were talking about before. So here's setup, right? And here's loop, right? And the Arduino IDE kind of tells you what is what, okay? So for example, it says put your setup code here to run one time, okay? So it's telling you right here, and this is a comment, right? It's telling you this is gonna run just once. And then this is your main code. This is the main functionality that your program has, and you're gonna put that in loop so that it runs over and over again, okay? So it goes ahead and tells you that, which is nice. Of course, we know that because I just talked about that. But let's go ahead and get this demo going. So first things first, as we said, before we talked about setup, we talked about, including libraries and defining things, etc. We don't have any libraries in this example because this is very simple. So we just have some pins that we need to define. So let's go #define. And the first one is the input of our switch, okay? So we're gonna go switch in 3, okay? So that might be an example of how you define something, okay? So you can see how that's working. Also, I clicked on my board here, so Arduino Uno, and then the compile is right here when I'm ready to run, and when I'm ready to actually run on the board, I click upload, okay? So let me switch back to the slides for just a second here so that I can show you exactly what we're gonna do, okay? So this is the circuit that we are going to be running right now, okay? So what we're gonna do is first, we're gonna start off simple. We're gonna push the button and make the LED turn on, okay? Very simple on-off type circuit. Honestly, you don't even need the Arduino to do something like this because it's so simple. We're gonna start off with that, and then we're gonna make it slightly more complicated. We're gonna make the LED blink, and we're gonna specify different blink intervals, okay? So that's kind of the main goal here. That's what we're trying to do. Okay, so let's go ahead and pop back over and make that happen. So we've got the first thing, so that we've got our switch. So that was that button. I'm gonna use a toggle instead of a button because that's what I have. But in the studio, if you physically go to the studio this week, you will see a button instead. Okay, doesn't really matter, different options. They do kind of the same thing. All right, so we've got our switch defined. We've said that it's on pin number 3. So once again, that's a GPIO pin. And I can check either the physical board, or I can go online and look up a pinout and see what pin 3 is on there. Okay, so we connect the switch to pin 3. All right, so now define LED out. That is gonna be pin 6. So what this is actually what the LED is connected to. So I'm gonna connect an LED to this pin, okay? I'll actually connect it in series with a resistor for the reasons that I specified at the beginning of this whole discussion. But yeah, so the LED will be on pin 6. That's what that means. We're telling the Arduino, okay, I'm gonna call pin 3 switch in, and I'm gonna call pin 6 LED out. That's all we're saying. All right, so I've just given them nice names. Okay, so commenting is /. So I'm gonna actually write that out, define pins. And then again, another comment. Now we're gonna define variables. Okay, so remember that's another thing I mentioned that we do before setup. All right, so I'm gonna specify this integer. It's called blink interval. Okay, so once we actually start making this thing blink, we're gonna change this to vary the period with which it blinks, okay? So that's the interval. We'll make that an integer. You can also make that a constant. Doesn't really matter. I'm just gonna leave it as an integer, but you could also put const int and then blink interval, okay? All right, let's move into setup now. So we've got everything defined. Now we can actually initialize our pins, okay? So to do this, so basically in here, we need to tell the Arduino what pin is an input, because we're using GPIO pins in this case. So we need to specify whether the pin that we're using is an input or an output, okay? So to do that, we're gonna say pin mode. So that is a function that the Arduino understands. So we're gonna say pin mode, and we're gonna say switch in, okay? So that's the pin that we're specifying right now. And in that case, remember I said that that's that button or the toggle in this case. So that is an input, okay? So we just put input. That's the key word that it knows. And then semicolon, okay? It will throw an error if you don't put a semicolon. All right, next, we have another pin. So we're gonna go pin mode, LED out. And in this case, like I said, this is our output. So we're gonna put that, output in all caps, okay? And then semicolon. And that's all for this code. It's very simple. In this case, we just have one input and one output. All right. Okay, so now let's get to the loop. So this is the thing that's going to run over and over and over again. Okay, so if we just want to turn our LED on or off, then very simply what we're going to do is we're going to check whether the switch is on or off, and then depending on the value of the switch, we will turn the LED on or off as well, okay? So first things first, we need to read the value of the switch. So we're going to set up a Boolean, which just means true, false, high, low. That's what a Boolean is. It's just got those two values, high, low, on, off, all the same deal, okay? A lot of times you'll see true, false, but in this case, we're saying high or low, all right? So we've got a Boolean, we've got switch value, and we're gonna use this function digital read, okay, to read the value of the switch. So remember, we called our switch in, okay? So that now we're reading that and storing that in switch value. All right. So now we want to write to the output, okay? So let's write digital write, and we're going to say LED out, and we're going to set that to be high, okay? Or rather, sorry, instead of doing that, because I would just always have it high, we're just going to set that to whatever switch value is. Okay, so switch value is high, meaning I press the button, then the LED will turn on. If not, then the switch value will be low and the LED will be off, okay? All right, so now let's run this code. So first things first, I'm gonna hit compile to check and make sure that I don't have any errors. Okay, so there we go, we're done compiling, no errors, so we're good to go. So now let's upload. All right, so we're uploading. And remember, compiling is actually sort of an optional step. You can just skip that and go straight to upload, but it's kind of nice to see whether you have any errors before you try to send it to the Arduino board itself, okay? So now that we've done that, everything's kind of set up. So let's go ahead and pop over to the Arduino here so that I can show you exactly what's gonna happen, okay? So on the Arduino, popping over to the demo now, you can see I've got my toggle switch right here. So that's the toggle switch. And you see everything's off right now. And we've got our circuit set up very simply. And then we've got the little LED all the way back here, okay? So I'm just gonna turn this guy on now. And there we go, our LED turns on, okay? Perfect. And if I flip the toggle switch the other way, then the LED turns off. All right, so that's all we're doing right now. So now let's pop back over to the code and make this thing blink. Okay, so that was the first thing. So that's pretty simple code. Let's make this a little bit more exciting. All right, so I'm gonna delete this whole digital write part. And now what we need to do is actually check whether the switch value is high or low. If it is high, then we'll make the LED blink. And if it's low, then we will turn the LED off, okay? So that's gonna require a conditional. You can see I'm saying if, else, right? So we just write that. If switch value double equals high, okay? And then we need to specify what happens. So we're gonna use curly brackets for that. So if, and then whatever's in curly brackets, if this is true, that'll execute, all right? So if that's true, then what do we wanna do, right? We wanna turn the LED on, we wanna leave it on for a little bit, then we wanna turn it off, and we wanna leave it off for a little bit, and then we wanna repeat that, okay? So that'll create that blink, okay? So it's gonna be on for a little bit, off for a little bit, and then it'll repeat, okay? As long as the switch is on. So how do we do that? So let's call digital write again. All right, so we're gonna say LED out. So remember, we just wanna go ahead and turn it on. So we're gonna say high, okay? Semicolon. Now we need to delay, okay? So we wanna leave it on for a little bit. This is going very, very fast. This whole loop is going very quickly. So if we just turn it off now, we're not even going to see the blink. The LED might just look slightly dimmer because it's just gonna go so fast, we will not be able to register the blink at all, okay? So we're gonna delay this so that it stays high for a little bit. So we're gonna delay it by whatever the blink interval is. That's what that value is for, okay? So we're gonna create a delay using this function delay, and then we're gonna turn it off, okay? So Right now we've got it at 500, that's in milliseconds. So this is off, or rather it's on for half a second, okay? So now we're gonna turn it off. So after we wait for half a second of it being on, we go LED out, low, semicolon, okay? Now we're going to leave it off for a little bit, okay? Because once again, if I just run this now, then what's gonna happen is whenever the switch value is high, it's gonna turn on. It's gonna turn on for half a second. Then it's gonna turn off for like, you know, a microsecond, and then it's gonna run again, or a millisecond or less, okay? So that's not good. We need to delay so we can actually see the blink. So we're gonna delay by the same amount of time, that blink interval. All right, there we go. Okay, now, so that's what happens if the switch value is high. I need to now specify what happens if the switch value is low, if I have it off, okay? So for that, I'm gonna say else, all right? And then another set of curly brackets. So remember, if the switch is not on, we don't want anything to happen. We just want the LED to be off. So we're gonna say that. We're gonna say digital right, LED out, low, okay? If I didn't have this, then what would happen is as soon as just one time I put that switch value on high, I would just get stuck, okay? We need something to get us out of this loop, all right? So that's this, digital right, LED out, low, okay? All right, now let's compile that, make sure everything's correct. Perfect, no errors. Let's go ahead and send this off to the Arduino now. So let's hit upload. It'll take just a second, there it goes. Okay, let's switch over to the physical demo now and see what's going on. So once again, same thing, I have it off right now, so let's go ahead and flip the toggle switch the other way. And there we go. So the LED is blinking. So you can see that, and I'll try to put that on this darker surface here so you can see it very clearly. It's blinking, so every half a second it turns on, then it turns off for half a second, just as we specified. So now let's just mess around with the blink interval and change it a little bit and see what happens. So I'm gonna change the blink interval to 100. So now if I change it to 100, that delay is much less, so it's going to blink a lot faster, okay? So I'm gonna go ahead and upload that. I didn't even bother to compile it. Of course you can if you want to double check. And you can see as soon as I did that, now the LED, so switching back to the demo here, the LED is blinking very quickly now, okay? So I can go ahead and turn that off, just like I could before, and then everything stops. And as soon as I flip that toggle switch back, the LED starts blinking really quickly again, okay? So you can see that happening right there. All right, so that's all. That's all for the Arduino demo. So we're going to switch back to the slides now. Okay, so now that we've gone over everything with Arduino, we were going to switch over and talk about Raspberry Pi for a little bit. So this is a very different system that can let you do similar things, but a little bit more functionality, okay? All right, so first of all, what is a Raspberry Pi? So today we're gonna be using the Raspberry Pi 4B. And so that is kind of the Pi shown on the screen here, okay? So as far as the Raspberry Pi is concerned, on the hardware side, right, we have the physical Raspberry Pi device itself. And in terms of memory, everything is gonna be stored on a micro SD card on a Raspberry Pi, okay? Your operating system, your firmware, it's stored on the SD card. So when the Raspberry Pi boots up, it will refer to whatever is stored on that SD card, so you can run different operating systems. So today I'm just gonna run the standard Raspbian operating system, but you can also run other things. So for example, you can run Octoprint and do stuff with printers. Lots of different options when you configure your Raspberry Pi. Okay, so that's memory. Everything to do with memory is on that little micro SD card. Okay, so pins, same deal. We're going to talk about the pins in a minute, but same sort of pinout situation, similar pinout situation as the Arduino. And then once again, we've got, as far as the interface is concerned, in this case, I'm actually connecting to my Raspberry Pi remotely. So that's a little bit different. I'm supplying power with a cord, but the actual connection is remote. So that's a little different. You can connect it directly. I've just chosen not to do that simply because I don't have the hardware that I need to do that on me right now. So I'm going to connect to it remotely, and I think that's a pretty common option. And yeah, so as far as software is concerned, this is really a lot more open than Arduino. So Arduino, we had the Arduino software. They have their own software. Raspberry Pi does not. Raspberry Pi, you can use any software, really. The most common thing that people do is they usually use Python. So that's what I'm going to do. But you can really run anything. You can run C, C++, Java, etc. Okay, this is very open-ended. It's really a full-on computer. And you can see on the screen here that we have like an image that looks like a desktop. That's because that's what the Raspberry Pi will show up as. And I'll show you that later. For the demo, it won't be quite as clear at first, but I'm going to show you the desktop as well, just so that you get an idea of what I'm talking about here. So it's really a full computer, though, is the main idea here. Okay. All right. So here's the pinout. So as far as the pinout is concerned, similar deal to the Arduino, right? So we have a variety of GPIO pins, and they're given BCM numbers, these pins. And so these BCM numbers are what I refer to these pins as in code. So I don't really pay attention to these pin numbers. I'm really concerned with these BCM numbers here, okay? So we can see we've got some I2C pins. So this is our data pin and our clock pin. We'll talk about protocols later. After we do this demo with Raspberry Pi, we'll wrap up with protocols. So these are going to be our UART, and then we've got some SPI pins as well. Okay, and we'll talk about what all that means. We've also got some 5-volt lines, some 3.3 volt lines, ground, same sort of deal as we had with the Arduino. Okay, so this is the pinout. All right, so now let's move on to the demo. Okay, so you can see I've got this desktop showing up here. We're not going to do it like that. This is one view. You can really code and interface with a Raspberry Pi in so many different ways, because like I said, this is really a computer. I'm using a remote connection, so I'm actually on the same Wi-Fi as the Raspberry Pi right now. But we're going to do the same thing that we did with the Arduino, but this time we're going to do it in Python, and we're going to use the Raspberry Pi. So let's go ahead and switch over. I'm going to use VS Code for the demo. Okay, so let's switch over to VS Code now. All right, so VS Code, I'm using an abbreviation. It's really called Visual Studio Code. Many of you may have heard of it. If not, this is like probably the most common IDE that is used for Python. Okay, so this is not just exclusive to Raspberry Pi in any way. People just use VS Code to code in Python and other languages as well. So that's why I chose to use it, because even if you choose not to use Raspberry Pi, you may use VS Code for something else. So that's why I went with this one specifically. And yeah, let's go ahead and connect to the Raspberry Pi. So what I need to do, I'm going to come down to this bottom corner here, and then I'm going to say connect to host. And then mine pops up immediately because I've already pre-configured it, of course. If not, then you need to add a new SSH host. So SSH is how we're going to communicate with this thing. But I'm just going to go ahead and click on this thing, and it's going to pop open a new window. And then it's going to ask for my password, which I'll type in. Okay, and then there we go. So now at this point, we have actually connected to the Raspberry Pi remotely. So now I can send code and interface with the Raspberry Pi through VS Code, which is pretty cool. So remember, this is like I'm connecting to a remote desktop, basically. Okay, I'm actually interfacing with another computer. The Raspberry Pi is a full-on mini computer. Okay, and that's going to become very clear when we pull up the code here. Okay, so what I'm going to do is I'm going to come over here and I'm going to say open folder. And here we go. So this starts to look like a computer, okay? It's got different locations, documents, downloads, desktop, because it is a computer. So that's the weird thing about this. It's really a mini computer, just with some pins, okay? Obviously, it's not as powerful as your laptop, but you kind of get the point here. It's really a mini computer. So I'm gonna go to my desktop. You can see I've got a few things here. This is what we're actually gonna be doing today. And so I'm just gonna open that. So this is what we're gonna do, and I'm gonna walk you through all of this as well. So this is all in Python, but this is what we're doing. I'm gonna go ahead and just delete all of this, and then we're gonna recode everything so that I can explain step by step exactly what I'm doing, okay? All right, so here we go. So remember, this is in Python, so this is a little different. Before we're coding on an Arduino, which is very similar to C or C++, now we are fully coding in Python, okay? So In Python, if you want to do comments, it's hashtag. That wasn't the case for Arduino, so you're just gonna have to get comfortable switching between languages a little bit here. So these are gonna be my import statements. So we're gonna start off sort of the same structure as the Arduino. Notice in this case though, I don't have like setup and loop and stuff like that. I have to create all those structures myself, okay? Because remember, now I have a lot more functionality. It's not restricted to what I was restricted with in Arduino, okay? I can do all kinds of things, okay? So import statements. So first things first, now we do need to get some stuff from different classes. So from this class called GPIO0, and you can see it's trying to autofill what it thinks I want to type out. And I'm gonna say import, I'm gonna import output device, okay? So there's my first import statement. Okay, so now from, once again, GPIO0, so I need output devices. I also need the functions for input devices. So I'm gonna do the same thing. So also from GPIO0, I'm gonna get input devices, okay? All right, so now we also need to create a delay. So we need to deal with time. Just so happens that that library is just called time, and I'm gonna import sleep is what I need, okay? So these are things that you would just look up, you know, how do I do such and such thing in Python, and you can get different classes that do different things, and you just need to import them at the beginning of your code so that VS Code knows where to access these things, okay? All right, and now we're gonna set up our variables / instances, okay? So set up variables / instances here. Okay, so first things first, I need to create an instance of output device, okay? So I need to actually create an instance of that. So LED, that's gonna be the name of my instance. So I'm gonna say LED output device, and then I need to provide whatever parameters output device needs. So in this case, you can see it's actually telling me that I need a pin, which is very nice. So that's one of the very nice things about VS Code is it will tell you things like this and actually help you code, okay? So it's telling you that it needs a pin. So in my case, I have this thing hooked up to pin 17, so I'm gonna go ahead and type that in. Remember, just refer back to that pinout diagram and connect things accordingly depending on the functionality that you need, okay? So that's it. All right, now we need the switch. So I'm gonna create another instance, this time of input device, right? And I'm gonna pass that pin. It's telling me once again that I need a pin. So that, in that case, I have this hooked up to pin number 27, okay? All right, so those are my instances of output device and input device. Now I also need just a variable, just like I had before, like with blink interval with the Arduino code. I need that time length or blink interval, whatever you want to call it, and I'm going to specify that here. So I'm going to say that's equal to 1, okay? And we will change that just like we did for the Arduino so we can see the LED blinking at different rates. All right, so now we've got all of our setup stuff done, but we don't have a loop structure in this situation. So we need to create that. So in that case, what I'm going to do to create an infinite loop, I'm going to say while true. So now the thing about while true is it's always true. So that means that once I get to this, I'm going to get stuck in this while loop. And that's the whole point. I'm just creating that loop structure that we had in Arduino. Okay, so there's different ways to do this. This is how I'm choosing to do it, so that I can create an infinite loop and pull the switch and send different signals to the LED, okay? So now, this will be my loop. Now, in Python, when you have a structure like this, like a while loop or for loop or an if statement, what you do is you just put a colon here, and then you can see it kind of did it for me, but I hit enter, and then I need some sort of spacing right here. I need this indent, okay? It doesn't matter the exact spacing of this indent, but you can see because this is like a smart development environment, it's just indented it automatically for me, so I would just leave it at that. But make sure every line needs to have whatever indent you specify in the first line following the colon, okay? Reality is VS Code's gonna do it for you, but that is how Python knows what is inside of while. So I don't have like brackets like I had in Arduino, and I don't have, you know, end like I have in MATLAB. In Python, this is how you do it. So different languages do this differently. This is just the way it's done in Python, okay? So what do I need to do? I'm gonna go ahead and skip the whole thing that we did with Arduino where we just turned the LED on. I'm just gonna skip that because you guys already saw that part. Let's just get right to the point. Let's make this thing blink, okay? So I need an if statement, right? We know that from Arduino. So we're just gonna recreate that functionality. So switch, and then we need to check if the switch is active or not, okay? Luckily, there's an attribute of switch. So we do .is active, is_active, okay? And that's just an attribute of my instance called switch, and it will be high if the switch is on, and it'll be off if the switch is off, okay? So remember, Python is a high-level coding language, okay? So that's why we see a lot of these abstract things like .is active, okay? Whereas in Arduino, it was like high and low, which is much more clear and low level. This isn't like that because this is a high-level language, so there's a lot more complexity and stuff kind of buried away in all these libraries, okay? A lot of functionality is kind of hidden from you. So makes it easier to code this because it just looks like English, right? It's like is active instead of high and low, but just keep that in mind, okay? So if switch.is active, so now I've got a switch statement or an if statement, so now I need another colon, right? I press enter, it automatically indents that again, so now I can do whatever I needed to do to make this thing blink. So in that case, it's gonna be LED, and we just do .on is what we're gonna do, and that is a function call to this function called on that's gonna turn it on, okay? So it's on. As we know, we need to delay it now, so we're gonna go sleep, and we're gonna pass in that time length that we specified above, okay? Notice there's also no semicolons necessary in Python, okay? That's another thing, just a little different from Arduino, okay? So no semicolons, no brackets, it's a little different, okay? So sleep, pass in time length, and then I'm gonna put a print statement on here so that we can see things in the terminal. So I'm gonna say switch detected on. It doesn't matter what you put in here, you can put whatever you want. This is a print statement. I'm just letting myself know every time I run that loop, okay? So there we go. All right, so LED.off. So now I'm turning it off, and then I'm gonna delay one more time. So sleep and time length, okay? All right, now we're gonna go else. You can see I automatically fixed my indentations for me. And remember, if the switch is not on, then I want my LED to be off. So we simply say that, LED.off, okay? And that's gonna turn everything off. So that's it, that's our code. And we can go ahead and run this. I'm also going to save it, so I'm gonna come up here and just hit save, and then I'm gonna go ahead and run, okay? And watch what happens when I run. So at first, nothing. So let's switch over to the demo now so that I can show you. And then we're gonna switch back and you'll see the terminal actually starts printing that print statement. Okay, so over here at the demo, I've got the same setup as I had last time with the Arduino. Okay, the only difference is, of course, now it's hooked up to the Raspberry Pi. So when I flip my toggle switch, you can see everything's off right now because the toggle is off. But if I switch it, everything starts blinking as we would expect. And if I switch back over to the IDE, you can see that it's saying switch detected on every second, okay? Because my time length, remember, in this case, it's in seconds. So 1 is 1 second, okay? And you can see it's just gonna keep on printing switch detected on over and over again, okay? All right, so now I'm gonna come back over to the demo, the live demo situation. I'm gonna turn that switch off. So now I killed everything, everything's off. And if I come back over to the IDE now, you can see it stopped printing, okay? All right, so now let's actually vary this time length, okay? And then we'll rerun this thing. All right. Okay, so now back over at the demo, I'm gonna flip that switch again, and now we can see that things are blinking a lot more quickly, and that's exactly what we expect, right? Because we decreased the delay, right, between on and off. So that's exactly what we wanted, okay? So let me go ahead and turn this off, and you can see everything stops, okay? Perfect. Okay, so that's pretty much it for how to code using VS Code. Now I'm going to show you something else that's pretty cool about the Raspberry Pi. So let me close this out. And I'm going to go to VNC Viewer, okay? And you can see here, once I open up VNC Viewer, I've got my Raspberry Pi right here. And you can see it's asking for a password. There we go. Okay, so this is very different. So I've now opened VNC Viewer, I've given it a passcode. Now this looks like a desktop. Now it looks like I've signed into a remote computer, and that's exactly what this actually is. So this is pretty cool. It's a little different from VS Code, but now I can kind of see all of my programs stored on my desktop. So remember, I opened from my desktop in VS Code. Now I can see what that is. So this is my desktop, and you can see, look at that. Now I've got my program right here that we just wrote. I can also come up here. This is like my applications. So I can come into programming. I'm going to go over Genie Programming Editor. I'm going to open that up. And look at that. So I've already got this open. This is the program we just wrote, right? So that's pretty cool. This is another way that you can program directly on the Raspberry Pi. So I can use VS Code if I want. For me, it's a little bit easier than using this whole VNC Viewer. But I can also just code directly on the Raspberry Pi, right? Because it is a full computer. So now I'm actually interfacing with an application on the Raspberry Pi directly. So you can use VS Code and send stuff to the Raspberry Pi, or you can open up the Raspberry Pi as its own device and use the applications that are actually on there. So this has a lot more power than the Arduino. Just because of this, there are a lot of applications stored on here. It's a full computer. You can see I can even access the internet on here. So you can see I've got internet access right there. So this is pretty cool. There's a lot of stuff in here. There is a lot that you can do with Raspberry Pi. Of course, there's also a lot that you can do with Arduino. And I encourage you guys to look up projects and mess around with this stuff more. But that's all we're gonna do for the Raspberry Pi demo. Okay, so now that we've gone over that, let's get back into finishing up our last bit of content, okay? So this is gonna be interfaces. All right, so we've talked about coding in Arduino and Raspberry Pi, and we've seen how to do that with our 2 demos that we had in this studio. But now what we might wanna know is, how do I communicate with different devices? Okay, so sometimes things are a little bit more complicated, right, than just having an LED or a switch. Sometimes my devices are a little bit more advanced and I need to communicate with them. But how do I do that? So there are different protocols. So we're gonna go over 3. The first one is I2C, okay, or I2C. It's also called 2-wire interface. It's the same thing, but this is our first protocol. So this is a very simple protocol. It's unidirectional, and I have my parent and my child devices here. So my parent device controls all of my child devices, okay? So these child devices could be sensors, they could be LED displays, etc. Okay? So all of them are connected in parallel. Okay, so the child device here gets the same information as the child device here, gets the same information as the child device here. They each get the serial data line, SDA, and the serial clock line, SCL. Okay, so the serial clock line keeps everything in sync. Okay, so this is a synchronous protocol. Okay, this is a synchronous setup. And the data line is where I transfer all of my data. Okay, so that's it. It's pretty simple. The parent communicates with all these child devices, and they're all receiving the same information. Okay, and you'll have to come up with your own protocol for if you need to interface with just one device at a time, or they can all just always respond to the same information every time. Okay, but that's how this works. That's I2C. Okay, just these 2 lines. All the children devices are connected to the same lines. All right. So now, what if I need to communicate with just one child device? Okay, that's where we get into SPI. So I2C is great because it's simple. there's just 2 lines. It doesn't require a lot of hardware. Serial Peripheral Interface, or SPI, requires a lot more hardware, but it gives me a little bit more functionality because of that, and it can also be a little bit better because it has unidirectional lines going in both directions. So to explain that a little bit, so we've got the parent device over here. This MOSI pin right here is my output, okay, from the perspective of my parent device. So the MOSI goes as an input into the child right here. Okay, and then MISO is going to be my input for my parent, which is the output for my child. Okay, so now I can communicate both ways. Okay, so it's still unidirectional on each of these lines respectively, but I can communicate in both directions. Okay, and then we still have the clock line, just as before, 0 o'clock. And then the main thing here that I want to point out is these select lines. So now these select lines, each child device gets its own select line. Okay, so this is how I can specify, okay, this child device needs to get this information, or this information is coming from this child device. Okay, so I can select different child devices. All right, so that's very important. That's a very important added bit of functionality that I now have, in addition to the fact that I can communicate both ways. All right. Okay, last communication protocol that we want to go over here is UART. So UART, so the other 2 protocols, remember we had a clock line. So they were synchronous. They were synced up to that clock. UART is asynchronous, okay? And you'll see that in the name, Universal Asynchronous Receiver Transmitter. And that pretty much sums it up. That's exactly what it is. It's asynchronous. We've got a transmitter that's going to receiver on the other device. Then the transmitter on the other device goes to the receiver on that first device, okay? So UART, you just have to come up with a protocol for how you're going to receive all of that information and at what rate, and when is the information coming, all that stuff. You've got to decide that in your protocol, okay? So a lot of times what you'll do, because now we don't have that nice clock line to keep us synchronized. So I could basically be sending data or transmitting data at any time, okay? So I need to know the rate, and a lot of times what I'll do is I'll specify some framing bits and some stop bits so that I can know where my data is, because otherwise it just looks like a stream of data continuously coming at me and I don't know what is what. So a lot of times we'll have a framing bit or a framing byte or a set of bits that tells me, okay, the data is about to start here, and then I'll have a set of stop bits that tells me the data is ending here. And so those will just be the same. I specify whatever that code is so that I know that this is the beginning of my data, then I'll have my data, and then I'll have the end of my data. Okay, so we sort of package data together into these nice packets so that we can understand where information is within each packet. Okay, so this is a little bit more complicated to implement because everything's asynchronous, but this is another very important, very common protocol that you will definitely see. Okay, so now a few more very quick things, and then we're going to stop for this studio because we've gone over a lot of stuff. It's a lot to digest, but this is just a quick note on drawing basically flow diagrams or block diagrams. And so you can see here in this example, this is like a lamp where you touch it and it turns on. That's basically what's going on. So you can see I touched the brass, it sends a signal over here. I've got some current limiting resistor here with the supply. Basically when I touch the brass, it sends the signal to the relay and then it turns the LED on. Okay, so the relay, the contacts come together and then it turns on. Okay, so that's kind of what's going on. That's not super important in terms of like what exactly is going on in this block diagram. What is important is just that you understand how to sort of write out these block diagrams. So get your components, lay them out, draw the signals that are transmitted between them or received between them, whatever the case may be. Draw out those signals. That's kind of the idea, okay? All right, logic flows. This is actually a lot simpler than a block diagram. This is basically like what devices are communicating with what, where is information going. Okay, so this thing actually detects planes flying over your house. That's what this thing is. I didn't make this. Actually, Ryan made this, our HDA Ryan. one of our HTAs. So what this is there's a plane, right? It's transmitting some information because there's radio and stuff like that going on. There's an antenna that picks up that information. That eventually gets sent to a Raspberry Pi. That gets sent to a computer once that whatever processing is done on the Raspberry Pi. Then there's a Python script, goes back to the Raspberry Pi, and then there's some sort of display, okay? So there's a basic logic flow. Where is information going, okay? That's all this is. All right, some final tips, okay? Okay, so useful resources. Adafruit has this whole learn page and a set of tutorials and stuff that you can go over. And then there's also a link here for some Arduino tutorials. You can check that out on your own time, but there's a lot of good information on those pages, okay? So now, YouTube tutorials, also very great source of information. Just look up all sorts of things about Arduino and Raspberry Pi and how to get started with them, okay? So, for example, I skipped a lot of the details on how to get set up with Raspberry Pi because we just don't have time to do it. I just kind of showed like some options for how to run code, but I didn't show any of the setup that I had to go through, but that's all stuff that you can look up on YouTube. Very easy to find information about these things because they're very common and people do a lot of stuff with them. You don't have to be an engineer to use these devices, and that's why they're so common and that's why they're so great. And there's all sorts of resources because they are made to be hobbyist friendly, okay? All right, so ChatGPT, you can use ChatGPT to do these things. It's a good source of information too. Just know, you know, sometimes it'll lie, so you have to vet the information for yourself. So yeah, but this is a good way to do things like how do I do X thing? ChatGPT can usually give you a quick answer if it's something simple if you're just getting started, okay? If you need to buy electronic parts, sites like DigiKey, sites like Mouser, these are common big names for part supplies. And also, we're here to help. So, of course, if you have any questions, come talk to us. That is what we're here for. Okay. Coding tips, these are general things. Honestly, you know, I'm not a CS person by any means. So take what I say with a grain of salt. These are actually tips from Tomo, who originally made these slides, another one of our TAs. And so, yeah, you can kind of see what they are. Googling is big. Reading documentation is big. If you run into a problem, look it up, go read the documentation for whatever you're trying to do, whatever functions you're using, whatever parts you're using, read the documentation. That is a big hint. No one wants to read documentation, but it's very necessary. And you'll be doing that on the homework this week as well. Okay. So, also, once again, ChatGPT can kind of get you out of some ruts in some situations for some simple stuff. Okay. Last thing, this is sort of just a quick disclaimer that, hey, yeah, we know there are a lot of other microcontrollers out there on the market. We've only gone over 2 things. We chose the ones that are probably the most common and things that you're going to use the most, but certainly there are a lot more. For example, STM32. If you continue in electrical engineering in your capstone, you will probably end up working with STM32 devices, and those are, you know, you work with those in C or even in assembly language, so it can be a lot different. There's lots of different devices. ESP32 is another one, etc. Okay, and there's a few more even on this slide. So we know there's a lot more, but we chose the ones that were probably the most common. Okay. And that's it. That's going to conclude our studio for today, for this week. I hope this was helpful and informative. I hope this one was also a little bit more exciting because we got to do some actual coding and getting things to blink and that sort of stuff. So got to build some circuits, got to see some code actually run in real life. And yeah, I hope this helps you guys get started on your projects for Project 3. That's kind of the whole point of the studios, is to a quick gear up for what you're going to be doing in Project 3 a lot more. So yeah, I hope this is helpful. Of course, reach out to us with any questions, and I will see you guys on the next review video. Thanks.